podcast is brought to you by LMU Munich.
Time. So let me just summarize what we did yesterday. So yesterday we started with the heuristic notion of a black hole, and then we defined it more precisely as a black hole is a space-time which has event horizon. So something like that. For Schwarzschild black hole is some kind of a sphere. In general, it can be not a round sphere, but slightly distorted sphere. And of course, this is only in the theta phi plane, but it's moving at the speed of light. If you looked at so we define the event horizon is as the stationary null surface For example, in the case of Schwarzschild black hole, it was a surface r is equal to 2m, and clearly it is stationary because it does not depend on time, which is the killing symmetry, which is so time, and del by del t was the killing vector, meaning a symmetry of the metric, which is time like at infinity. So stationarity simply means that with respect to a symmetry of the metric, killing vector simply means it's a symmetry of the metric doesn't depend on it, which is time like at infinity. Obviously, t is time like at infinity. This equation does not depend on it, so it's stationary. But the non-trivial thing was it is also null. That means it's moving at the speed of light. And basically, once you cross this horizon, so this causally separates inside from outside. And when we really analyze the structure, we found out that spacetime doesn't really end at r is equal to 2m, but it looks like that. There is a singularity at r is equal to 0, and r is equal to 2m. So at each point there is a sphere. That sphere on this diagram, this is the RT plane, and constant r slices were going like that, and constant t slices were going like that. So far away, time slices look like the usual time slices, and the observers are going as usual observers, freely falling observers in flat space. But as you come near the horizon, there is, and this is causally separates because signal here cannot come out. Signal cannot come out, so that causally separates the inside. So that is now for us the definition of a black hole. And then we figured out how to compute the various parameters of the black hole, such as the temperature. And I'm just going to remind you using the Reissner-Nordstrom black hole. What we did, that we had a metric we discussed yesterday the Schwarzschild black hole, but let me now describe the Reissner-Nordstrom black hole. So, in fact, let me call this factor A. There is a factor A. So, it is generally of the form A of r dt square plus A inverse of r dr square plus r square d omega square, and AR for the Schwarzschild black hole was just 1 minus 2m upon r. But here basically the mass gets contribution from the electrostatic energy, which as you know is q square upon r. So, just on dimensional grounds you can see that it has to be q square upon r square. So, q square upon r has dimensions of mass. So, q square upon r square. So, this is the Reisner-Norton metric, and the event horizon basically practically. So, we are basically now going to consider stationary black holes. This is also stationary black hole in that its metric does not depend on the time. You can consider more complicated event horizons, but for our purposes we will always consider stationary black holes. And the event horizon in this case can be easily located by finding the 0 of this, and it has two zeros. R is equal to r plus and minus, square root is equal to m plus or minus square root of m square minus q square. So, instead of having two horizons, it has two, instead of having one horizon, it has two horizons, and q equal to 0, you get r plus is equal to 2m, which is the Schwarzschild case. And then we consider a more special. In general, m has to be greater than or equal to q, and for m equal to q, r plus is equal to q. Something wrong here. I hope I have written it right. Yeah, okay. So, this is what we call extremal black hole. And then we figured out how to compute the surface gravity by analyzing r going to r plus geometry, and you write it in the form minus rho square kappa square dt tau square dt square plus d rho square plus r plus square d omega square, and we can figure out kappa and the temperature by writing the metric in this form, and then the temperature, Hawking temperature, was h bar kappa upon 2 pi, which for this black hole takes the form square root of m square minus q square divided by So, this was one of the exercises in the tutorials that we did yesterday. And the interesting thing is that, of course, at m is equal to q equal to 0, you get Schwarzschild black hole. Kappa is equal to, temperature becomes 1 upon 8 pi m. But the more interesting example that we wanted to consider when m was equal to q, when the temperature goes to 0. And then we saw that the two laws of thermodynamics, the whole point of going through this discussion of surface gravity and temperature was that now the two laws of thermodynamics are satisfied, that you have dm is equal to T ds, and ds is always greater than or equal to 0. These two laws are satisfied once we include these quantum effects. Once we put this h bar, the temperature is non-zero, and you get a second law and first law of thermodynamics, like for any other system. And the entropy, you can just differentiate this dm and T, and you can figure out what is the entropy, dm divided by T, and the entropy is pi r plus square, which is basically area upon 4, area of the horizon divided by 4. So, area is equal to 4 pi r plus square, and this has a finite limit. This goes to pi q square. and the temperature goes to 0. So, we said that this is a nice system to look at, because it is a stable, it is not decaying anymore, it is not dynamical. And the question that we posed for ourselves yesterday, which we are going to address today, is to explain the black hole entropy. The problem is to find, is S is equal to k log omega or k log d. And of course, for extremal black holes, I can just forget about the advantage of extremal black hole is now it only depends on Q. Of course, this question is more general, but we will ask it for extremal black holes. And this question is, as I explained, is of fundamental importance for anybody who is interested in quantum gravity, because basically you have general relativity on one side and you have quantum mechanics on the other side. And here you have the black hole solution, and this you want to think of as a collection of, we are going to think of it as some kind of an ensemble. So, the black hole has a very nice property that it's like looks like an elementary particle. That there is this no-here theorem, which is sort of mentioned in these notes, that tells you that a black hole solution is completely specified by just specifying its mass and its charge and its spin. This is very unlike the solution around the sun. So, if you had the sun, the gravitational field around it depends on the valleys and mountains on the sun and how the matter is distributed on the quadrupole moment on the sun. But once it collapses to form a black hole, it forgets all the information about the quadrupole moments. All the moments are not important. So, this property of the black hole was very interesting, and that led people to think of the black hole as some kind of an elementary particle. But the correct thing is that now we understand the black hole should really be thought of as a thermal ensemble, because the thermal ensemble is also specified just by specifying energy and a few conserved quantum numbers. So, this is the picture that is going to emerge, that a black hole, because it has this thermodynamic properties, is actually like a thermal ensemble. Even though it is just a geometric object, once you put in quantum mechanics, it's secretly a thermal ensemble. So this side is thermodynamics, and this side is statistical mechanics. So this is very much like a gas in this room, or air, whose entropy you can measure, and here we have some kind of a molecular structure. And that's the reason why this is very important, because if you want quantum gravity, which connects the two, a very important link is provided by the Bekenstein-Hawking entropy, that you have entropy and here you have log of dq. So I can set k equal to 1 from now on. So now I have told you how to compute the left hand side. So the rest of my lectures are now going to about how to compute the right hand side. And in fact, we can do better, because this is in the limit, it turns out, when we will find, in fact, that S of q generically will have corrections. It will have something like pi of q square plus corrections, which we can go as of order 1, some number, let's say a1 plus a2 divided by q square. What we have found is just the leading answer when the large charge limit. But in fact, there is a very beautiful generalization of the black hole entropy called the Wald entropy, which allows you to compute not only the first pi q square, but also the subleading corrections. And our goal is going to be now compare that with log of dq. Log of dq will also have some, we will find pi q square plus b1 plus b2 upon q square plus etc. But let me call this in fact a0, b0. And the idea, one of the very nice tests that you can make is to calculate all the AIs. So, the goal compute AIs and BIs and show or check I'm being a little bit heuristic here. Yeah, but on dimensional grounds, there is a L string that is going to appear. There is a string coupling, string length that will take care of the dimensions. So, for now, actually, from now on, you can think of Q as just integers. So, everything is now I will choose units such that h bar is equal to g is equal to kappa is equal to 1, and from now on we will only talk about integers, because then entropy, if you take k equal to 1, is just a number. It does not have any dimensions. If you put Boltzmann constant equal to 1, it is just log of d, where d is a number. So, our goal is to find this number s of q on the left hand side and compare it with the d of q on the right hand side. Yes. So, that is one of the reasons why it should depend only on q square, for example. Are there any other questions? Yeah, there can be a log term. It's a good point. So, there can be a log term also. There can be log q square terms in general. So, I am just writing it very schematically, but I think the general program should be clear to you, that the program is that, as we saw, we had to work quite hard to figure out A0. What did we figure out? For example, we found out that A0 is equal to pi. All this work of Hawking and Bekenstein of going over 40 years was basically to figure out that A0 is equal to pi. Now, we want to figure out what is A1, A2, A3 and so on, and we want to find some system where you can actually count B1, B2, B3 and B0, and this is where supersymmetry comes into picture. And the reason is that we will basically this side will be, roughly speaking, some string coupling constant G string, let me call it, much greater than 1, and this side will be some other coupling constant much less than 1. So, what we are actually going to do is compute this on left hand side and the right hand side at different regions of the moduli space, different values of the coupling constant. Of course, this is a very bad thing to do. I mean, as you know, if you have studied quantum electrodynamics, at G string coupling constant very small, it looks like free quarks. At coupling constant very large, it looks like pions and protons and neutrons. So, what you compute on this side may have absolutely nothing to do with what you compute on this side. So, making such a comparison would look completely foolish thing to do, except in the situation where you have supersymmetry, and because of supersymmetry, we can actually do this analytic continuation in a reasonable way. Allows you to continue going from small to large. And over here, the system G string is equal to small, the same object with the system with the same charges, the configuration of the same charges, the same charge configuration is represented by a collection of loosely bound strings or momentum, or it can be D-branes, or it can be more exotic objects like Kaluza-Klein monopole, NS branes, etc. And the important thing is that they are loosely bound. So they are bound states, but something that you can analyze in perturbation theory. And then we can therefore compute. So given some charge q, in the BPS, for the supersymmetric, the extremal case, the mass is determined by q, so only need to specify q. You specify the charge and compute d of q. And then use supersymmetry to analytically continue this. That's going to be the objective. Very good, good question. So you have to actually specify basically there are two classical limits, as you know, even in electrodynamics. You can take the limit, the particle limit or the field limit. So you can either approximate the electromagnetic second quantized field as electric and magnetic fields or as photons. And to make it actually, it's not, in this case it's actually, maybe there's a simpler way to say that. Let me explain. Sorry, it's probably. Yeah, the short answer is that notice that the Schwarzschild black hole has the factor 1 minus 2 gm upon r. So whether Newton constant is small or large depends on the mass. So basically, if for some practical purposes, so gm defines some length, gm is the quantity of interest. So for an object of some mass, if I can ignore gm, let's say much less than, suppose the gm becomes of the order of the Compton wavelength. So if the gm becomes less than some length scale, some fundamental length scale like L string, then 1 minus 2 gm upon r can be, for lengths larger than the string length, can be approximated as 1. So basically the geometry is not back reacting at all. And g, as you know, Newton's constant is proportional to g string square. Is roughly g string square divided by L string. So there is a clear understanding of what we mean. For a given mass, you make g string so small that you can just drop this factor. So even though the string is there or some object is there, the d brane is there, it does not have any gravitational back reaction. In that sense, the gravitational field around it is very weak. So that's the limit. Are there any other questions? Okay, so now our goal is, let me erase this. What I want to now discuss is a bit of supersymmetry, because I got the feeling yesterday that not everybody has seen supersymmetry. And I also might have confused things because what I was calling supercharge Q looked like the electric charge Q. So let me just say a bit of supersymmetry. So we are going to now do this whole story for n equal to 4 supersymmetric compactification. In d is equal to 4 in 4 dimensions, and that is obtained by considering what is called the heterotic string compactified on T6, and then you have M4, which is the Minkowski space, or you can have type 2b string. So if you have not seen these things, don't worry about it. There are some names. Compactified, as you know, string theory lives in 10 dimensions, but this is K3 cross T2. This is another 6-dimensional manifold cross M4.
Why would you compactify a heterotic string on a torus? You won't get chiral fermions.
Yeah, I don't want chiral. So as we said, we are not now worried about getting the real world out of string theory, right? So what I said was that string theory exists in many phases, like water phase and liquid phase and so on, vapor phase and so on. And of course, to compare with the real world, we have to land up in the correct phase or the correct vacuum of the theory. And that problem has proved to be extremely difficult, and basically string theory is stuck in trying to find the correct phase in which string theory should be landing ourselves. The real world is in which phase, we don't know. But as I said, the questions relating to black holes and information loss and the interpretation of the entropy in terms of counting of microstates is independent of the phase. So if we found some phase of string theory in which this is not true, when S is not equal to log omega, we can just throw away string theory and forget about it, because then it is inconsistent. So because we don't know which phase the theory is in, we want to focus on questions that are universal, and black hole entropy happens to be one of such questions. That's the reason why black hole entropy, many of us are taking it seriously. And that has also led to things like holography, which Son has discussed. I mean, very similar considerations having to do with second law of thermodynamics lead you to the concept of holography and analyzing black brains. So our objective therefore is to look for a very simple phase. So it's a bit like in the case of water. I mean, as you know, the liquid phase is very complicated. It's strongly interacting. If you can analyze the theory when it's in the gaseous phase, then you can analyze as an ideal gas, and you can do the computations much more easily. So supersymmetry is sort of the analog of that, that if you take n equal to 4 supersymmetry in 4 dimensions, your model is much more under control computationally, and you can do detailed computations. But the questions that we are asking are of a universal character. So we are sort of hoping that the lessons that we learn from here are general and not specific to this particular compactification. Okay. So n equal to 4 supersymmetry is specified by apart from momentum and p mu nu, and so as you know, there is some commutation relations of this which goes as p mu, and then the mm commutator is, this is the Lorentz Poincare algebra, and pp commute with each other. Supersymmetry just extend this by adding some objects qi alpha, where I is going to go from 1 to 4, which is why it is called n equal to 4, transforming as an SU4, 4 of SU4, and alpha is going to go from 1, let me call this A actually, since I'm going to use it, and alpha is going to go from 1 to 2, transforming as a spinner, wild spinner, a 2 spinner of the Lorentz group, SO1, 3, or spin 1, 3. And supersymmetry algebra simply extends this by adding anti-commutators. In particular, you will have, and then there are complex conjugates of this, which are Q alpha dot, A dot. Can everybody see this, or? So A dot is in the 4 bar of SU4, alpha dot transforms, you can call it q bar if you like, the conjugate spinor of spin 1 comma c. And the commutation relations are very easy to write down, and you must have seen this in textbooks if you have studied a bit of supersymmetry. But let me just write it since not everybody has seen it. But basically it looks like q alpha a, q bar a dot beta, or alpha dot if you like, is equal to 2 p mu sigma mu alpha alpha dot delta a dot and q alpha a q beta b. And sigma mu are basically the matrix 1 and sigma, the Pauli matrices. And there is a similar thing for q bar. Q bar is equal to z bar. So this is called the supersymmetry algebra, and it is called n equal to 4 because A takes values from 1 to 4. And the nice thing about this, that just like for this algebra, we had a massless representation and a massive representation, as we discussed. A photon has 2 helicity states, and vector boson has 3 helicity states. Here we can actually diagonalize this matrix. You can write ZAB in the form Z. It's a 4 by 4 matrix, but you can sort of put it in the form Z1 and then Z2, a block diagonal form with some epsilon tensor using the SU4 symmetry. And this, therefore, we have 2 central charges, Z1 and Z2. They are called central charges. Central charges in that they commute with everything. They are called central because these things commute with everything else. They don't have any commutation relations. And the important thing is that the supersymmetric analog of the extremal condition is the following. Okay, maybe I should just write one more thing here. We will find that Z1 and Z2 will turn out to be functions of the charges, like electric charge and magnetic charge. And also scalar fields, are called moduli. So in the simplest case, for example, if you just had roughly to keep in mind, Z of Z1 would be like Q. This Q is to be not confused with this supercharge which has indices. This our Q is just the electric charge. And oh. This is going up. Sorry, it should be going down, and this should be going up. Oh, sorry, I wanted this to go up. Sorry. Okay. The main point is that notice that the supercharges satisfy anticommutators, and therefore they are like fermionic oscillators. And basically, by taking a linear combination of those, you can define fermionic oscillators. Let's call them B. We can define basically B, some operators B, B dagger, which can be either 0, well, which will turn out to be proportional to m minus z1. So we will assume, without loss of generality, z1 absolute value. z1 is a complex number, incidentally, and this can be bigger than z2, and we just order them. And typically what we will find is that B dagger, you can sort of define B as a linear combination of various q's. So for example, you can take q11 plus q bar 1 bar and so on, some linear combination, which is explained in the notes. To rewrite these anti-commutators and go to the rest frame, so in the rest frame only P0 will matter. So you basically have mass and central charges. So you have some anti-commutators, some QQ bar anti-commutator is equal to the mass, and some QQ anti-commutator is equal to the central charge. And we can reorganize it in such a way in terms of some new oscillators B, so that it looks like B dagger is equal to m minus z, and some other B1 dagger is equal to m minus z, B2 dagger is equal to 1, etc. You can organize this whole thing in such a way. And then you can see that now this allows you to prove a bound. This implies a BPS bound, that because the left hand side is now positive definite, m has to be equal to z bar. And clearly there are various possibilities. If m is greater than z bar, then I can have, basically by rescaling, I can set B1 dagger is equal to 1 by some appropriate rescaling. And then I will have so many fermionic oscillators. And if I am starting with 16 charges, because notice that you have, or 8 complex charges, you have 4 and 2, 4 times 2. I will have, in general, in this case, we will have several situations, non-BPS. You have 8 complex fermions, oscillators. Huh? Sorry, when this is strictly bigger, this is the non-BPS case, you will have 8 complex oscillators, and the representation will be 2 to, now the representation of this algebra is very easy. For each oscillator, you will get an up and down. You can have either spin up or spin down. So each B1, this algebra is represented by some up and down, such that B2 dagger up, down is equal to up, etc. Yeah, so this is just mod Z1. So I have ordered things in such a way that Z1 is bigger than Z2. So it's clear that in the case when you have non-BPS, then of course you'll get a largest representation, which is 2 to the 8, which is the 256 is it's called the long representation. And in fact, there will be 3 cases of our interest. So you can do this analysis more carefully, and it is explained in the notes. But my purpose, I think, in these 3 lectures, it will be impossible to really derive everything in detail. So what I have done is that the derivations you can find in the notes, and I'm just going to tell you the results and some way how to go about it. Wow. Sorry. So there are 3 cases. One is a long representation, non-BPS, 256 dimensional. All supersymmetries are broken. So you have basically 2 to the 8. Complex supersymmetries. So if you have 8 complex supersymmetries, you have 8 oscillators. That's the basic idea. And this has m greater than then you have something called half BPS. Okay, you have quarter BPS. And it's called quarter BPS because it preserves 1 quarter. So 1 quarter of 8 is 2 and breaks 6, the remaining. So it's 2 to the 6th dimensional. So it's 64, and this is called intermediate representation. And this happens when m is equal to z1 of q, but this is strictly greater than z2. Q and p. I mean, in general, it will be q and p. This also depends on q and p. And then finally, you have the shortest representation, which is called the half BPS. And this is 16 dimensional. This is called short. And this is m is equal to z1 of pq is equal to z2 of pq. So at least the logic should be clear to you that because z1 and z2 are equal, some more oscillators will have 0 appearing on their side. So basically, you'll preserve, when you say preserve supersymmetry, that means the commutator of those guys is 0. And therefore, you'll preserve 4, half 8, preserve 4 and break 4. And so that's 2 to the 4. Is this clear? Now I can operate all 3 at the same time, getting better at this. Okay. Okay. So now the only other thing that you need to know about string theory, and this is again we will discuss in the tutorial if you have questions, because if you have not seen string theory before, then it will be very difficult to explain it. If you have seen it, then you probably already know it. So I'm just going to state the relevant properties of string theory for our purposes. So this string theory, the low energy Lagrangian of this string theory, this compactification, so far what we are doing is basically just group theory. This is totally valid also in quantum field theory or anything. It's not, we are not using string theory. We are just doing, there is some commutation relations and you are trying to find representations. So this is completely group theory. And as you know, there are representations, massless representations, massive representations. In this case, there are super multiplets. So we have to get not only the bosons, but also the fermions. And there are 2 types of massless representations. One is called the supergravity multiplet, which is also 16 dimensional because it's massless. It's basically a simple example of BPS, because you have 0 charge, 0 electric charge, 0 magnetic charge, and mass is 0. So the BPS bound is satisfied. So it is 16 dimensional, and it has the metric and phi AB sorry, not phi AB, what am I saying? A mu AB, these are anti-symmetrized, and then there is a field called lambda, complex field. So you can count, if you count the physical degrees of freedom, this is 2, physical degrees of, something is wrong. Yeah, this is 2 into 6, that is 12, and this is 2. So, that is 16, and actually the supergravity multiplier is 16 plus 16 because you have to take CPT self conjugate. So, you have 16 plus 16 dimensional representation, and 16 of them are bosons. So, the bosonic fields are basically the metric tensor, a scalar field, and 6 because AB is anti AB in this means that these are antisymmetric 6. The 6th representation of SU4. So, basically supergravity multiplet has 16 bosonic fields, the metric tensor 6 fields, and what is called the axion dilaton field. And basically this S, the expectation value of this field is the string coupling constant, G string square in 4 dimensions. And the second representation that we need to know is the vector multiplet, which is CPT self conjugate, so it is only 16 dimensional, and it consists of the bosonic fields. Of course, in this there are some fermionic fields which are called the gravitini, etc. Gravitinos or gravitini and dilatini, etc. Whereas here we will be only concerned about the bosonic fields. Here you have some field A mu and phi AB, so 6 scalar fields, and these are 2, so that is equal to 8 plus fermions. And the nice thing about supersymmetry is that the low energy effective action at 2 derivative is completely fixed by supersymmetry. For a given number of, for fixed, once you specify NV, which is the number of vector multiplets. And that is the reason we want to take supersymmetry. Supersymmetry is so powerful because, as you know, supersymmetry means that the Lagrangian has to be invariant under supersymmetry transformations, and the content, the field content is basically completely specified for you, and more importantly the Lagrangian is completely specified for you. This is completely, so in general if you had lots of scalar fields and lots of U1 fields and the metric, you could write down a very complicated action, right? Because you could write down action like, so let me write down the action for you in a moment. Okay, so I think I should send this guy up and this guy down. Huh? Quarter BPS fields. Yes, indeed. I mean, we are going to actually talk about quarter BPS states, in fact. Can you have So that's non-BPS. When everything is broken, it's non-BPS. You want that everything is preserved. Yeah, that's just the vacuum. Yeah, you cannot have. Yeah, you don't have any, because if you break all supersymmetries, then all the fermionic oscillators have commuted of 0. So it's just a one-dimensional representation, which is the vacuum. Yeah, you can have one-dimensional representation where all the oscillators are just 0. So B1 acting on the vacuum is 0, B1, I mean, you can have, well, yeah, so there are no states which preserve all supersymmetries. I mean, there are no non-trivial states. I mean, okay, so if your vacuum does not spontaneously break supersymmetry, then clearly it preserves all supersymmetry. So that's an example. Sorry, what did I do here? So the nice thing about supersymmetry is that once you specify the number of vector multiplets, then the Lagrangian is completely specified. And in fact, it has a very nice group theoretic structure that the low energy action or low energy equations of motion have a large symmetry. Global symmetry. For NV, we'll take NV is the number of vector multiplets. And it is of the form SL2R and ONV, O6NV R. And in fact, the fields take value in these cosets SL2R divided by SO2 and this divided by the scalar fields O6 cross ONV, and they transform. For example, lambda goes to A lambda plus B divided by C lambda plus D, where A, B, C, D are in this SL2R. Similarly, these other fields phi AB, if you have NV of them, we will have phi AB with some index I. And in fact, it turns out that you can sort of combine them into a matrix M, capital M, Mij, which is a matrix of SO or O22, 6, ONV6 matrix with some properties like MM transpose, M transpose is equal to M, and it preserves ML, M transpose is equal to L, where L is the, this you can think of as a generalization of the Lorentz group. It has minus, okay, let's go write it NV cross R6. So many minus entries between NV cross NV minus entries, and so many plus entries, 6 cross 6. This is also for the scalar fields in the vector multiplet. So if you recall, the vector multiplets have 6 scalar fields, phi AB. And if you have NV of them, then you will have 6 times NV. And you can check that the dimension of this coset space is 6 times NV times 6. You can check that the dimension of this group manifold you know, right? So you can do, so for example, the dimension of this group manifold SL2R is like SO3, it has 3 dimensions, and SO2 is 1 dimension, so 3 minus 1 is 2, and that's one complex boson. That's just the upper half plane. So lambda lives in this upper half plane. And this is some other coset space, and you can see that in general you know that if you have ON, then it has dimensions n minus 1 divided by 2. right? O3 has, or O4 for example, has 4 times 3, 4-dimensional Lorentz group has 6 generators. So this has so many generators, you can just do a counting, you'll find that this has dimensions 6 times NV. So basically, these fields parameterize this complicated coset space, and the fields lambda parameterize this upper half plane. Now, n equal to 8 has more fields. This is the n equal to, why does it have 16 plus 16? Because, see, basically you have spin 2, then when you act with supersymmetry once, you'll get spin 3/2, that is the gravity now. But you have many, many supersymmetry generators, because you don't have just, you have 8 of them. So you keep on acting, and then from 3/2 you get to spin 1, then you get to spin 1/2, then you go to spin 0. Sorry, you have 4 of them because this is short multiplet. You see, 4 supersymmetries are preserved, so you only have 4 oscillators, 4 B daggers if you like. So starting with 2, you act with the 1 B dagger, you'll get 3/2, then another one you'll get 1, then you'll get 1/2 and 0. You have 4 of them. So you have to go down by steps of 4. But this is not CPT conjugate. So basically you get spin 2, 3/2, 1, 1/2, 0. Okay? This is your vacuum, then you act with B dagger, another B dagger, another 3 B daggers and 4 B daggers. Okay? But this is not CPT requires that in a quantum field theory you have to CPT, so it requires you to have -2, -3/2. You cannot have just a one helicity, that's not allowed in quantum field theory. So if you have and this 0 plus 0 is your lambda field, and these 3/2 and these ones, there are actually 6 of them. So this you can work out. This is a standard thing that you can look up, for example, Weissenberger. If you had 8, you will actually keep going. You'll get 8, 3/2, 1/2, 0, -1/2. You don't need to add this CPT. You'll get a CPT self-conjugate representation. Any other questions? And now what is nice is that notice that in fact for our case heterotic on T6 is supposed to be dual to type 2B on K3 cross T2. And this is one of the very remarkable discoveries of the mid-90s. The 2 string theories which look very, very different in 10 dimensions. You see, heterotic string is totally different from type 2B string in 10 dimensions. There is absolutely no connection between the two. But you compactify on different manifolds, and these 2 theories turn out to be exactly identical. It's a strong weak coupling duality. And one of the pieces of evidence is that the massless action has to be the same. And very surprisingly, when you do this reduction, you find n equal to 4 supersymmetry. And that's because heterotic string had 16 supersymmetries in 10 dimensions. On a torus, you don't break any supersymmetries, so you get 16. Type 2B had 32 supersymmetries in 10 dimensions, but K3 breaks half of the supersymmetries. K3 is not just a flat space like torus. So you break half the supersymmetries and you get 16. So you get the same number of supersymmetries and you get NV is equal to 22. So altogether, we have 28 gauge U1 gauge fields. So we will have the metric, in the end you will have the metric G mu nu, A mu of I, Mij and lambda. This is your massless field content of the 2 theories, where I goes from 1 to 28. So it's very simple. At the end of the day, if you just open some book on string theory, you don't need to know this. Supersymmetry is so powerful, that's the reason why we are taking this large supersymmetry, that you specify the number of vector multiplets, the content of the theory is completely fixed, and moreover the action is also completely fixed. The symmetries of this theory are completely fixed. But what is interesting for our point of view now is that instead of having just one electric charge and one magnetic charge, we will have a vector and a vector of magnetic charges. So let me call this charge vector gamma. So Q is a 28-dimensional vector of integers. These are the electric charges, and P is another 28-dimensional vector, and these are the magnetic charges. Again integers as required by Dirac quantization condition. They will satisfy Dirac quantization condition. So for this you have to do a computation, and this is explained in the tutorials that start with the field content of heterotic string theory, compactify on T6, you will get altogether 28 vector fields. This is very easy to see. So you start with 10-dimensional, you know the content here, Gmn. When you dimensionally reduce it, this will go to G mu nu plus G mu m. So if you have T6, you'll get 6 of them, like that, and you just count. It's a very straightforward exercise, and this is one of the exercises in the tutorial. If you don't know it, we will work it out in the tutorial so that you. So what I want to tell you is that it's not very complicated. You don't need to know a lot about string theory, because supersymmetry basically determines everything for you. So once you figure out how many vectors are there in your spectrum, you have figured out everything. Then supersymmetry tells you everything. Yes? Yeah, because it's Calabi O2. Supergravity, absolutely right. So far what we have done does not require string theory at all. String theory is now going to come in a very soon. So one of the ways string theory comes in, forgot. I should check in my notes. I just wanted to write down for you the Lagrangian. Just to give you an idea, the Lagrangian is completely fixed by the string theory, by the supersymmetry, and it looks something like this. Because I forgot to take the printout of the remaining. Just a second, give me a second. Yeah, the Lagrangian looks something like this. I just wanted to write it, flash it by you. It's there in the notes that you will get today. It looks something like d4x square root of g determinant minus g times the S field times the minus g actually, Rg plus 1 upon S square g mu nu del mu S minus half del mu A plus 1/8 g mu nu trace of del mu m L del mu m L minus G mu nu prime, G nu prime, F mu nu I, L m L I j, F mu prime j, minus A divided by S, G mu prime, G nu prime, F mu nu L I j, F mu prime j I. Okay? So, everything is known to you here. Lambda is equal to A plus IS, and G is not the metric. Oops, sorry. G is equal to S times G mu nu. This is called the string metric. Sorry, the other way around. E to the minus 2 phi is probably the other way around. Okay, this is called the string metric, and this is the Einstein metric. So, L, as you know, is this minus 1, 22 cross 22, and plus 1, 26 cross 6, and M was some matrix, and lambda. So, this is a completely specified, fixed by supersymmetry. So, this is what we mean by why supersymmetry is so interesting, is because look at this complicated Lagrangian. Now, in principle, I could have added all kinds of things. All these coefficients are fixed. You cannot mess with it. I could have added some random function of A upon S here, or I could have added something else here. And that would have been very, so in general, you would have had, if you did not have supersymmetry, a lot of freedom to choose and we don't have any more that freedom. And so, our objective will be now, so now we can take this Lagrangian and try to find these black hole solutions. And instead of the black hole now having just one charge, one electric charge, like the Reisner-Nordstrom, analogs of the Reisner-Nordstrom generalizations. I mean, they are generalization of the Reisner-Nordstrom black hole, specified by the charge vector gamma is equal to QP. And this charge vector has a very nice property that it transforms as a doublet of SL to Z. And as a 28 of O22,6 Z. So, SL to Z means that you just take these matrices A, B, C, D, which they were real, you make them integers. Why do they make them integers? Because these are all integers. It's a matrix of integers, and one of the important properties of string theory, which is called duality, is simply the statement that the string theory is, if you change the moduli, the change moduli and charges transform under some duality group GZ leads to physically identical theory. That's the statement of duality. Duality means that duality is basically is a Z2 symmetry, but now in string theory the symmetry group is actually much bigger. It's a non-abelian generalization of Z2. Duality simply means one theory is equivalent to another. But here what we are saying is that the whole slew of theories, different points in the moduli space with different charges. So, for one of the this is called S duality, and this is called T duality. And you can see it's called S duality because it changes electric to magnetic. For example, S duality. This is a very deep statement, and if you have not, nowadays I think you just take duality for granted, but it's actually, you have to realize that it's a highly non-trivial statement that, for example, QP can go to electric and magnetic can get interchanged, and lambda can go to -1 upon lambda. This is one of the duality symmetries. And you can see that under that, the coupling constant is strong coupling, weak coupling gets interchanged, and electric magnetic charges get interchanged. And the statement is that these two theories, one theory which is at strong coupling, string theory at strong coupling, which we don't know how to really analyze because we only know string theory at weak coupling, how to do whole sheet perturbation theory. The non-trivial statement of duality is that these two theories are equivalent. And for our purposes, the simple statement is that the charges transform in some linear representation of this duality symmetry. Now, this simplifies the calculations a bit if you use these duality symmetries. And then the objective is that our objective in the next 15 minutes will be to get started on the statistical mechanical side of things, which we have not so far done. So, find a black hole BPS black hole solution with charges PQ. Find its entropy. So, this is something that this is a two derivative Lagrangian. It's a complicated Lagrangian, but actually you can solve it. It's not so complicated. And in fact, we will describe methods using the entropy function, which actually simplifies the computation much more. So, this problem has been solved, and the solution is a generalization of the Reisner-Nordstrom black hole. I mean, just like you had not actually solved Einstein's equations to get the Reisner-Nordstrom black hole, but you know how to do it. You just write down Einstein's equation and solve it. If you do the same, what you find is that the entropy depends now, instead of being pi q square, it depends, it has to be duality invariant. So, it's q square p square minus q dot p whole square, where q square is like qi lij qj, roughly speaking. Okay, actually you have to put it in slightly different basis, but okay. So, this is the answer, and then the problem is so again you appeal to supersymmetry, that these are BPS black hole solutions. So, therefore, the mass in this case, and in fact there are two types of black hole solutions now. As we have said, there is a short representation and intermediate representation. So, what happens, in fact there are two types of states in this case, and if you recall, half BPS, which meant that the mass is equal to Z1 of QP is equal to Z2 of QP, which is 16 dimensional, happens when Q, the vector Q vector, is parallel to this. You can check. So, recall, let's say Q and P are some 28 dimensional vectors in some big lattice. It's a list, you have 28 integers, and that defines a lattice, right? You can have a lattice. So, Q, yes, you have some lattice of charges. So Q is some vector like that, and P could be some vector like that. If they're parallel, that means if P is parallel to this, then it turns out that the state is half BPS, and the mass is equal to that. And our interest will be quarter BPS when Q is not parallel. And this is the entropy formula for this is quarter BPS black hole. Because you can see if Q is parallel to P, then Q square P square is the same as Q dot P square. So this would be 0. For half BPS, so these are the quarter BPS. This is your 2 and this is your 1. Now there is a very interesting story with this half BPS black holes, which these are called small black holes, and I will just make a parenthetical remark here. Interestingly, these are called okay. Yes? Yeah, they are equivalent to extremal black holes. But they are analogous to extremal black holes. They are not exactly like the Reisner-Nordstrom black hole, because recall Reisner-Nordstrom black hole was a solution of Einstein-Maxwell theory. There were no scalar fields around. In this problem, we have scalar fields in the problem, and that changed the solution. So you have to solve the whole system again, find the black hole solution, and find this kappa parameter, and you will find that the kappa parameter is 0 if P is parallel to Q. Okay? So now we turn to the problem. Find D of PQ. That's where string theory now enters the story. Now I think I still have about 7 or 8 minutes, and now I'm going to start a simpler computation and explain the real computation tomorrow. So what we are going to do today, this I had given yesterday as an exercise, but unfortunately we didn't really have enough time to discuss it. So I want to now describe to you how the counting is done in string theory. And we are going to illustrate that by counting half BPS states. So for the half BPS states, the entropy side is a little more complicated because you have to find this small black hole with the string scale horizon. But the counting is actually very easy, and that's going to be good enough for our purposes for today. So a state with charge q you can represent it as perturbatively. And in heterotic string, there is a very simple, nice set of perturbative states. You recall that we had heterotic string on T6. We can take T6 to be equal to T5 cross S1 and wrap a string, a heterotic string, wrap it W times and carries momentum okay. So these are your two charges, because from the 4-dimensional, for the 4D observer, you don't see the internal circle. So there is a string wrapping W times carrying n units of momentum, but the 4-dimensional observer will see it as a point particle with two integers. So you have two integer charges. Okay, and we want to find the number of states d of nw. And in heterotic string, this computation is particularly easy because it's perturbative string theory. As you know, heterotic string it's called heterotic because the left moving and right moving are different. So it lives in 10 dimensions. And so suppose you have a string going up like that. Let's call this coordinates x and y. The string is going like that. So there is a y coordinate of the circle and the time coordinate. So you have last 2 dimensions, and you can only have transverse directions xi. So basically you have 8 xi's which can oscillate as t minus y. You have both left movers and right movers. And in addition, the heterotic string theory has some fermions which are transformed in the spinner of SO. This is SO8 vector quantum numbers. It turns out this also is, there is an 8-dimensional spinner representation. And in addition, there are there are 16 internal bosons, and that's why sometimes it is said heterotic string is 26-dimensional bosonic string on the left and the superstring on the right. 26 because this is 16 plus 8 plus 2, that's 26 if you count the light cone directions, and here it is 10 dimensions but you have supersymmetry. So supersymmetry is carried by supersymmetry generators carried by right movers. And now you have so many oscillators. Of course, you can expand these fields. In terms of oscillators, a n I e to the minus I t minus y divided by r n, etc., plus complex conjugate. So your counting problem is reduced, and the energy, as we saw, so basically you will have so many oscillators on the left and so many oscillators on the right. you will have oscillators AIN on the left hand side, a collection of oscillators, and here you will have A tilde IN on the right movers and S tilde AN. Is that clear? And energy, these are just free oscillators, these are just harmonic oscillators, and these are harmonic oscillators which is fermionic. And but BPS state, keep the right movers in the ground state. And that's because each oscillator has some occupation number. You can excite that oscillator into some excited state. So you can specify the occupation number NNI, N tilde NI, NIN, and S, let's call this occupation number M, MA tilde N. And the simple computation is so I think I will go maybe 3 or 4 minutes over time. And as we saw yesterday, if we just said let's look at the single oscillator, the energy is going to be something like N upon R. The left moving oscillators minus N tilde IN. You have to sum over I and N. Sorry, this will be plus, and the momentum, the charge Q is going to be N upon R, or the momentum. And basically the BPS condition means is the same as the extremal condition, that find the configurations for fixed P, for a given P, because notice that this is going to be exactly this N is your charge that you're going to recognize for the black hole. So what you want to say is that I have fixed charge. Now let me try to minimize the energy, because the BPS state is the minimum energy. What energy can I have? It's clear for a fixed N implies that E is equal to P and N tilde equal to 0. So basically you have only left movers excited, right movers are 0. Similarly, you can see that S tilde N is equal to 0. So your problem is reduced to finding N I N and N I N such that the total charge Q, in fact I can put this R on this side and measure the total. And let me change this N to maybe N prime. So find that I want the total charge, the quantized charge to be N. N is equal to n prime I plus n tilde I n prime summed over all the configurations. So this is the problem. Basically, it's like fixing some energy for some oscillators. And this problem, of course, in the canonical ensemble is very easy to solve. That you introduce a chemical potential conjugate to n. So dn, the number of, find all possible configurations, and dn is the number of such, is the degeneracy. We can just take w is equal to 1 for simplicity. Okay? So it's easier to go to the canonical ensemble, where you compute z of beta, which is trace of e to the minus beta of this quantum number p. Of course, as you know, because of the 0 point energy, the oscillations of the oscillators, you actually get a -1 here. The energy turns out to have a -1 because of the 0 point energy. So there is a -1 that you can put here. And so this is basically, for each oscillator, I will get something like 1 plus, suppose each oscillator of frequency I will get something like q to the n plus q to the n plus q3n, qkn. These are the oscillation numbers. And this, as we know, will be 1 upon 1 minus q to the n. For each harmonic oscillator, for each I, or capital I or small I, where q is equal to e to the minus beta. And so that implies that z of beta is equal to just, there is a q because of this -1 and to the power 24, product over all n going from 1 to infinity. So each direction gives you 1 minus q to the n product over n, and there are 24 transverse directions because this I goes from 1 to 8 and this capital I goes to 1 to 16. And that 16 incidentally is related to, that's the E8 cross E8. If you must have heard that the heterotic string has E8 cross E8 symmetry. The rank of E8 cross E8 is 16. So it's the 16 dimension, those 16 dimensions are related to the rank of the gauge group of heterotic string. But for your purposes, you could just think of it like a real string oscillating in 24 directions, 24 transverse directions. And obviously you have 24 free bosons, so this is a partition function. And it's very easy to compute now d of n. You can just do an inverse Fourier transform. Laplace transform, inverse Laplace transform. And amazingly, you can show that this goes as exponential of 4 pi square root of n for n much larger than 1. And this is something that maybe we will discuss in the tutorial today. And this is something that we want to compare with the entropy of the black hole. Of course, what we will do tomorrow is that we will now try to do the same thing. This was half BPS black holes. So therefore, the entropy is 4 pi square root of n. And in fact, if I put the w, it actually will be 4 pi square root of nw. You can work it out. It's not so difficult. For quarter BPS, and this matches with d of q. I didn't tell you how to compute the entropy of half BPS because you needed higher derivative corrections, but it matches with this counting that we did. So this is actually rather amazing that one side is some complicated black hole solution of this complicated Lagrangian. It has nothing to do with strings oscillating and some, right? A priori, these two things are completely different. What string theory tells you is that these are related to each other by just changing the coupling constant. So the black hole is nothing but this configuration of little strings oscillating, and this harmonic oscillators oscillating at weak coupling. You just crank up the coupling, the gravitational coupling constant becomes large, it collapses to form a black hole. And therefore, because the BPS states don't get, they are not renormalized and so on using this arguments from BPS, the number of states at weak coupling must be the same as the number of states at strong coupling. And therefore, the degeneracy that we have computed at weak coupling, which is going as exponential of 4 pi square root of n, must match with the exponential of the entropy. And that tells you that entropy is. Now, the similar computation in quarter BPS case is actually much more complicated, and it's much more interesting also. And that's what we're going to discuss next time. But the basic idea is simple, that you try to reduce this complicated system to basically a bunch of free harmonic oscillators. And in this case, we reduce the problem to 24 collection of harmonic oscillators. So if you can figure out this number 24, which came from the perturbative string, then you know basically how to compute, because then you can evaluate the partition function. If you had fermions, then you would have gotten something on the numerator, because fermions typically will give you something in the numerator. So basically, you need to figure out how many bosonic and fermionic oscillators there are in this system at some weakly coupled regime, and that allows you to do the computation. And that's what we are going to use for this quarter BPS ions in n equal to 4, that now this problem has basically can be reduced to just a computation of harmonic oscillators. Okay, I think I'll stop here. I have gone over time already.